Okay, there you go.
Okay. Here we have the hydrodynamic diffraction analysis that we did the last session, and now we add the hydrodynamic response, which is related to time domain analysis of marine structures. We should click on it and hold it and drag on the solution part. And here the hydrodynamic response is added to hydrodynamic diffraction, and the outputs of the frequency domain, like the hydrodynamic coefficients, are imported into the time response analysis. And now we click on the setup part. As you can see that the hydrodynamic response is added to the hydrodynamic diffraction. Okay. For the analysis settings, you should take this computation type on the time response analysis, and you have to set your time, start time and end time. The start time is 0, and the time step we assume to be 1 per 10, and the duration means the end of your time duration. I mean, we can choose it like 300 seconds. And just this option, these parameters should be defined for the time response. And here on the hydrodynamic response, you should click and insert. You have some options like deactivating the freedoms, such as the heaving point absorbers, that they just have a motion in the heave direction. You can deactivate all freedoms except the heave motions. You can click on the deactivated freedom, and you have to choose your structure and deactivate the freedom along the x-axis, y, rotation about x, rotation about y, and rotation about the z-axis. We assume to model the heaving point absorber, for example, and we just have the heaving motion. After that, we have the some options for modeling the current, wind, and the irregular waves. You can define these parameters based on your design and model. But I don't work with the current and wind, but you can see these options in for the exact details on the user manual. You can see that we have the wind with different spectrum. It may be useful for modeling the wind turbines, and the irregular waves also with different spectrums, like Jones, Fab, Pearson, Moscovich, and Bert Schneider. And also you can add, if you have a time history spectrum, you can import it from here. But here we can assume to have a Jones Fab spectrum, and wave range, you can add it by frequency or period. I put it on the period. And here you should define the significant wave height, the gamma parameter, and the peak period. The significant wave height, for example, with is comma we assume to be 3.3, and the peak wave period with 8 seconds. And you can see that it creates the spectral based on your inputs. And it's just this. And now click on the solve and to see the results. Okay, on the results, you can see the motions, forces, and the connections. If you have connections, and after this part, I show you the with a cable modeling that you wanted me to last session about the tension of the cable. But if you want to see the structure motions like the structure position, you can click here, structure motions, positions, and actual response.
Hussein, just a question. I'm trying to
Yes.
do wave field here, but I got an error about alpha out of range in Jones-Swap spectrum. Do you know what that is? With the same values as you used.
What happened again? Can you explain?
Alpha
Here.
out of range in Jones-Swap spectrum. That's the message for me here.
Out of range.
There are two Jones swap that you can choose, Matthew.
Yeah, the wave and the alpha, but I choose the AJAS one, same one.
Okay.
I didn't face with this problem, but
okay, let me just try once more here. Just a second.
okay.
Let's see. So
we want the results of the position, I mean the motion of your structure, and as we assume the structure is only have the heave motion, and so here we have to put the component on the global Z. And also we can have if we have if we define a connection point here, we can have change this reference point or motion relative to other points that we defined before. But here is align the center of gravity here, and you can see that this is the results, and also I think it's synced in the water, and maybe we don't modeled our wake as exact parameters, but this is the motion of our structure. Okay. About the forces, like the wave excitation forces in the time domain, we can also have the diffraction and Froude-Kirillov forces, and these are just the results of the time domain. But if you want to see the cable tension, we have to define a connection point here on our structure, and also a fixed point on the seabed. Connection point. You can see the connection point and also an fixed point. The water depth is 100 meters. Okay. And on the connections, insert connection cable. We should define the start and end connection points. The start is on the structure and the end point, excuse me. The connectivity type should be a fixed point to a structure. The start point on the seabed and the end point is the connection point on the structure. And we assume to have a stiffness piece. Okay. Also, you can this type of cable that we modeled here is linear, but you can have other types of cables. And the nonlinear catenary type of cables is the cables with different stiffnesses. For example, you can have a cable with 10 sections and with 10 different stiffnesses. It can be done, and just on the time domain solution, you can solve your model. Okay. On the connections, you can see the cable forces and the whole cable forces or section tension. Section tension, I think it's related to the catenary cables with different sections stiffnesses. But the whole cable forces, we can see. Okay, the tension and value tolerance. Here is the tension of your cable during the time domain analysis. Also, you can see an animation of your model here to see what happens during the 300 seconds. Okay. And another useful thing that for modeling the PTO that I said, we can have the stiffness and damping matrices added to the structure and see the results. And now I suppress the cable. We don't need it, and also the fixed points. We can delete it. Okay. For modeling the linear PTO on the ANSYS, that is the only way for modeling the PTO in ANSYS. I mean, if you want to model a hydraulic PTO, it may be so complex. You need to model it on the ANSYS Fluent or CFD and connect it to the ANSYS OCO, and it may be so complex. But the only way is to model a linear PTO with just a stiffness and damping coefficients. You can add a stiffness. You can see that it is there's a stiffness matrices for the type of our model that we model here is the point absorber and with heaving motion. We can assign the Z stiffness. For instance, with 15,000. And also we can have the damping.
Why would you want to do that? Why would you add extra damping?
Here we can see we can model a PTO, linear PTO, power takeoff. And after we model the PTO, the results of the time domain with, the motions, the velocity and accelerations, they can import it to the formula of calculating the power. And you
Okay,
can,
got it.
yes. Let's see that. Sorry for this problem. Okay. We add the stiffness matrix and the damping matrix with the. Okay. Okay, now first we have to do the frequency domain and then the time domain analysis.
Let me ask you something that is like way back there about the geometry again.
Okay.
One question that I have is, you calculated the inertia values based on the formulas for the geometry, right?
Yes. Yes.
So my question is, you're assuming that those formulas assume that the geometry is a solid, but the actual vac is like a sheet
Shell.
of steel or something like that. So doesn't that interfere with the result and invalidate them?
I don't know why this has happened, but in the ANSYS Aqua, I see it in the theory manual of the Aqua. The moment of inertia should be based on your whole geometry with solid part. If this results show us in here, we can see that the differences between the mass you calculated and the mass that the ANSYS calculated. Because after the hydrostatic analysis of the ANSYS, it shows us the differences. And also the way that I calculate based on that formulas, they don't have any differences and they have the same numbers. But I don't know why this is happened.
Yeah,
The
okay,
exact
so
result.
yeah, I got this problem because I did it in a different way, and ANSYS started to complain about, hey, your mass is 0.5% different from my own. So yeah, I don't know. I can ask you later about this manual, but you can go on.
Okay. How did you calculate your mass?
So if you know how deep the geometry goes into water, that's the same process as you told yesterday. It's about how much of it is immersed in water. So if you use the water density and that volume, you can get to the mass. So, but the thing is, I was trying to use the static structural toolbox to calculate the inertia values for me, because that's a way that Ian here on the lab teach me how to do. We're still trying to figure out how this works, but it's a much better way, because if the geometry is complex, it doesn't matter because it
Yes.
calculates for you. So I'm trying to figure
Certainly.
stuff out. So, but in this case, I got like a 0.5% difference, and ANSYS started to complain about that.
Certainly, for the complex geometries, the structural analysis may be more useful and efficient.
Yeah.
but I have problems with that in the defining the density of the water for our structure.
Oh yeah, so in this case, to get it to work, I had a
Yes.
problem, which is to use that, I have to define the thickness of the material, and
Yes.
I can't get this to work. So I have the number here that I calculated. So what I did was I was trying values for the thickness until I got close enough. So that's the only way that I could do it, but it's not very nice.
How you define the thicknesses of your structure? I mean, what is the number that you assumed?
Yeah,
How
so
you assume this one?
so you have the density of the water and the volume that is immersed. So from that you get the mass that you need, the structure needs to have. So if you go to the structural toe box, if you play a little bit with the thickness, you can keep changing it until the value comes to the value that you calculated. So that's how I did it, like a trial thing. But it's not very nice. It's not like automatically.
Okay. Now we assign the stiffness and damping matrices to our structure to model the PTO. And here we can see the changes in the motion of our structure. And that is the result of the effect of the PTO. And now you can extract this motion and the velocity into the formula of the calculation of the power, and you have the stiffness and damping coefficients, and so you can calculate the power based on the formula. It's just this. But again, if you want, you can if you want to have another ways for modeling the PTO, you don't have to model the stiffness and the damping coefficients. You just need the hydrodynamic diffraction analysis, I mean the frequency domain analysis. And after that, you can export the hydrodynamic coefficients like the added mass, wave excitation forces, and the radiation damping parameters into the time domain analysis that you have to done it for by another programs like open source codes like Vexim that have a lot of features for modeling the wave energy converters. Here just this, and if you have any questions about this part, you can ask me.
Oh, no, I think that's fine for now. I have to try it again to see if I got some problems. I still get an error trying to do it here about the values for the alpha. I don't know why, but maybe I can try again later.
Here, I don't know what happens, but you should try it again. The thing is, ANSYS have a lot of bugs. I mean,
Yeah.
we have many problems during my models, and I faced with a lot of challenges. It's very hard to model something ANSYS.
Yeah.
Okay. If you have another things, you can ask me. And
So if you want to do an animation out of the simulation, how do you do that?
animation, you mean here? Yes, in the time domain.
Yeah, exactly.
We just on the solution, click on the insert result, and excuse me, we have it on here. I think. Yes, on the solution, click on the insert result and the animation.
And the duration of the animation is the setting inside analysis settings, right?
Yes, you can see on the playing, and you can see the motion of your structure during the 300 seconds.
Yeah, the screen for us is a little bit bugged out. We can't see the animation you're playing, but I
Yes.
got the idea. That's no problem.
Okay. Another important thing is when you have, for example, two body wave energy converters in the time domain analysis. I mean, the two bodies should be connected to each other, and if they don't connected to each other, you may have faced with some errors here that said your structures have a far distance from each other, and the analysis may be stopped. I think they have to be connected to each other, for example, with a cable or with a fender. Also, you may be model the PTO with a fender and a cable. For the two body wave energy converters, you can model a cable and with a fender to connect your two structures to each other, and model also the PTO, because the cable has a stiffness and the fender has a damping coefficient, and they can also model the PTO. It's another way for modeling the PTO, but it may be a little complex.
Okay, nice. So is there something else on the time domain that you can do, or is that basically it?
It was just this,
Okay,
the general
it's
things.
much easier. I mean, much less
Yes.
details than the frequency domain. That's nice.
Yes.
All right, so
just the outputs is the motion of your structure, or maybe the velocity. You can add it to the power calculation formula and calculate your output power. It's just this.
great. Another question about the geometry itself. When you
Yes.
are drawing it on SpaceClaim, you have to turn on the option to share the topology. Do you do that
Yes.
for each part separately, or just the component that has both parts in it?
We did it for each component separately. I mean, look, as you can see here, we have two components. One
Okay,
for
hang
the
on. I
float part.
can't see your screen yet. Hang on just a second
Okay.
to see if it updates here.
If I want, you can.
Are you on SpaceClaim or?
No,
I don't
I'm
know.
in the Aqua.
Okay. Okay,
Yes.
now I think it's okay.
Okay, I go to the space scanner and let's see what happened if we didn't put it on the share. But in this case that I explained, we don't face with any problems because as we can see in each component, we just have one shell. But if we detach this part, for example, as you can see, we have three shells. In this situation, if we import this geometry into the Aqua, we faced with a problem. Now we can see if the share topology, we put it on the none, and we have three surfaces. Now let's see what happened. And
So in my case here, I got the boy component, and inside it I have the two parts. And on the boy component, I put it to share. So is that wrong?
no, you just have to put it the share topology on share, because it I mean it it assumed that three surfaces, for example, in this situation, that three surfaces are just one shell, and they have one motion, for example, and in the results they have one result. And now you can see that we didn't put the share topology on the share, and we have three surfaces on one component. And now you can see that it show us with the red lines and about the QTF matrices. You should put it on the share. You can see, yes. Now you can see that again we have three float components. But we have to assign a point mass just for the float part. We have to assign one point mass for the float part. But we have three float parts here for each surface. So we can't define a one point mass for our structure. Here we can see the differences when you don't put the share topology on share, and when you put it on the share. Here is another problem that we have.
Okay. Nice. Something more, or that's it?
Okay. Yes, that's it.
All right.
If you have any questions.
José Fredo, do you have any questions? For me, that's all fine.
It's okay for me.
Okay.
Mateus, is this the last class, right? If I got it.
Yeah, for now it is.
Yeah,
But
just want to say, Hossein, I'm giving the baby steps on ANSYS, as you know. So, is there any problem, like in the future, if I have some small doubts, to try to contact you again and ask questions? I mean,
No.
it's not even necessarily like to have classes like that, but perhaps just to get in touch and send an email with some punctual questions. Is that okay for you?
Yes, you can contact me every time that you want, no matter what time is it.
Thank
I'll
you.
be
Thank you so
available.
much.
Something more to tell you about. Yeah, I think that's it. So I will have a look again at the classes here, try to do something, elaborate a little bit more on the idea, then I can come back to you via email.
Thanks, yes.
Okay. And
if it's possible, you have any links for the recordings that you have?
Okay, I think.
Yes, send me the links.
Yeah, I can
download.
I can send it to you.
Thanks.
Okay, so that's it for me.
Have a good day.
Okay, so see you later then. Thank you very much for
Thanks.
your time and all these
Same
classes.
for everything.
Have a good day. Thanks.
Okay, see you later.
Bye.
Bye bye.
Bye bye.